sedimentology who does not know his work, right? And Bob is going to present an overview on STRAITS today.
Okay, so thank you, Pirette, and thank you, Sergio, for inviting me. And perhaps, well, Sergio got me interested in STRAITS more recently, so maybe he regrets it. I'm not sure. STRAITS, and I've called it the new frontier in tidal sedimentology. When I was young, there was a lot of work on continental shelves, and ultimately it turns out a lot of that work actually is what I would now consider to be work on tidal straits. But most work on tidal environments has focused primarily on estuaries and deltas and lagoonal complexes along the shoreline. And Sergio recently has got us all to realize that straits can be very important depositional environments. He's focused primarily on these tide-dominated examples because of the proximity to the famous Strait of Messina. And he's developed this fantastic model. I like this model very much. I liked this model very much when I reviewed the manuscript in which it was presented. I was very sympathetic towards it. And I'm sorry that I have to now maybe find some quibble with details of this model. The weakness, perhaps, of this model, from the sort of the more fundamental basis of creating a facies model, the whole basis of creating a facies model is to distill away the unique features of individual environments and concentrate on the generalities. This model, as Sergio, I think, will admit, was based almost exclusively on the 3 examples that I've listed there. That's a very small database. And even the amount of data that exists for those examples is not very large. So that perhaps attests to Sergio's wonderful imagination, being able to make such nice models from such little data. So I was a little worried by this small database. So I decided to undertake a review of modern straits as sort of the basis on which the rest of you could go forward to develop better models. There are 33 examples in this list. If you can look through there quickly, the names are all at the bottom. They cover both northern and southern hemisphere, from nearly subpolar to tropical latitudes, arid and humid climates. There are over 400 named straits if Google is to be believed. So this is only a small subset, and yet it still was a substantial job to try and synthesize this information. The range of dimensions, just to give you some indication of the variability of straits, if you take a very broad view of what a strait is, they range by 2 orders of magnitude, or maybe almost 3 orders of magnitude in length, width, and depth. Some would, of course, be very concerned with perhaps calling Mozambique Channel a strait, but I wanted to have something at the upper end number for this analysis. This work has been published, now just recently become available on the GSL website in the volume that Valentina and others are editing on straits. It's open access, so you can look at this variability of straits. From my analysis, I would say that the diagram there on the screen of a single constriction flanked by 2 larger bodies of water is what I would refer to as the basic morphological building block of straits. For many people, it is what a strait is. However, in many straits, including this example from the Strait of Magellan, this is a longitudinal depth profile, the red arrows indicate the existence of 5 constrictions along the length of what I think we all would think of as a single strait. And so multiple constrictions can occur stacked end to end to form extremely complicated examples. In this particular strait, this end is extremely tide dominated. It's one of the handful of hypertidal areas in the world, but the tidal energy is dissipated by the time that you get to about this point, and this is all influenced by wind-driven circulation and some density stratification because of the colder and warmer water. So very complicated environment. For this talk, I've decided to pick on 3 topics of increasing spatial scale or temporal scale to examine in terms of things that I don't think we know enough about yet in terms of the dynamics and the sedimentation within straits. So much of this is sort of an outgrowth of my review rather than being actually in it. Oops, sorry, wrong button. Are tidal currents overemphasized? Sergio has been such a fantastic advocate for tidal straits that many of us think of straits as being tidal environments. Is that universally true? I think they actually have been. Maybe that's not the right message to be given at this meeting, but you have to be realistic. What is the architecture of the deposits that are formed by straits? And I'm talking mainly about these sort of deltaic-like bodies that occur on one or both sides of the constriction. And at the largest scale, what is the stratic organization of the successions in which strait deposits occurred? And that one I'll talk about at least. So, processes. In my review, I've found that straits in the broader context have 4 main possible types of currents. And I'll go through each of these in turn. There are oceanic through-going currents, density-driven circulation, either estuarine or inverse estuarine. So estuarine would be inwards at the bottom, outwards at the top, and this is outwards at the top, inwards at the top, outward at the bottom. Tidal currents and meteorological currents. So, a strait that I think many people would think of, perhaps, if they know these things, would think of as oceanic currents is Bering Strait between Alaska and the dreaded Russia. And this is a branch of the Kuroshio Current, which is locally along this coast called the Alaska Current. It's due to a water height difference of several centimeters to maybe a decimeter and a half between the Arctic Ocean and the North Pacific Ocean. Another strait that is strongly influenced by oceanic circulation is the Straits of Florida. This is what's called the red arrows of the Florida Current, which evolves into the Gulf Stream. And there are many features in this strait that show the evidence of this current. There are all kinds of contourite drifts, there are sediment waves, there are even dunes created in sand in some of the shallower water parts of this strait. Another set of straits that have or are dominated by oceanic circulation are those in Southeast Asia. There is a large-scale wind pattern that drives water across the equatorial Pacific Ocean. That causes super elevation of the water levels in the Southeast Asia here. And all of these straits, every one of these straits and many others that I haven't mentioned, all have consistent flow in the one direction. And this has generally been referred to as the Indonesian through flow as a major element in the global oceanic circulation. Even Torres Strait, that is generally believed to be tide dominated, experiences something like a 5 centimeter per second residual flow from east to west because of this Indonesian through flow, which can't be ignored in the larger scale picture, as we'll see later. Moving on to density currents. These are caused by differences in density between the water body at one end and the water body at the other end. One of the nice examples that I put in because of Jesper Bartholdi, who lives just right about there, I believe, isn't that right?
Yes.
And it's the Kattegat. And there has been some nice work done in a 2020 paper by Haid and others that's looked at the density stratification through that area. The Øresund is straight right at Copenhagen, and you can see this dense water that is flowing down into the Baltic Sea, and the water coming out of the Baltic Sea at the surface, the fresher water. And some of these currents, as we'll see later in the talk, can reach substantial speeds. Another one that might be better known is the Strait of Gibraltar, with the saltier water of the Alboran, or broader Mediterranean Sea, that is exiting over the Strait of Gibraltar and cascading down through the Gulf of Cadiz, eventually patches from the seafloor at around 1,000 meters, and flows along the southern margin of the Iberian Peninsula, and then with water flowing inward at the surface. These currents, again, can exceed a meter per second and can do substantial transport of sediment. Tidal currents. You'll see lots of examples on this because I know many of these areas quite well. There are, of course, lots of straits that are dominated by tides with strong tidal currents, so that we have the Strait of Messina, and this is the Golden Gate Inlet, which is the entrance to San Francisco Bay. These are two of the examples that Sergio has used. There's another example that I had to put in from the Bay of Fundy, the minus passage, minus channel. Tidal current speeds here have been measured up over 10 meters per second. And of course, in my consideration, La Manche is also a strait. It's just a big, wide one, with the constriction primarily being at the Strait of Dover, although the bedload parting actually occurs here, not at the location of the most narrow point. But there are many of these tide-dominated examples. Now, a point that Sergio has made that I decided to follow up on in my review was the correlation, if any, between tidal range and current speed, because there's a tendency to think that big tides mean big currents and small tidal ranges mean small currents. Well, that's not the case. The R² value here is far from significant. I've labeled some of the outliers. This Johnstone Strait is part of the complex network of straits that separates Vancouver Island from mainland British Columbia. 7.7 meters per second has been recorded in that strait with a tidal range that's only around 2 meters. And yet you get also some straits like Menai Strait with tidal ranges that are nearly 7 meters, where the maximum current speed is just only slightly over a meter per second. So there's a wide range of values. Meteorological currents is something that I knew very little about when I started this review. Going back to Bering Strait, these diagrams, this has got current speed on the this axis with flow to the north above the central horizontal line, flow to the south below it. And you'll see that most of the velocities are to the north because of the overall oceanic flux. However, that is extremely erratic record. The bottom diagram shows the volume flux in Sverdrups, as a volume measurement that oceanographers use. And the middle panel here is the wind speed taken at a nearby site. I've just highlighted 4 particular wind events. There, and this one. And you can see that they are corresponding with peaks in the velocity. And so that this highly erratic current record is entirely due to meteorological forcing, wind and atmospheric pressure differences. Now, I don't know that any of us would take that particular record as looking particularly tidal. It looks sort of random, which is what we might expect of meteorological forcing. But nevertheless, this is what causes the formation of elongate, dare I say, tidal or meteorological sandbars, meteorological dune fields. They've been described as tidal in the literature, but they're probably formed by meteorological currents. This is going back to the Kattegat again. I showed you this diagram again, but here are the velocities in meters per second at the various points along. And this panel was taken when there was a landward directed surge that was meteorologically generated. And you'll see that the speeds are up over half a meter per second, maybe reaching up to 80 centimeters per second in this direction. But this section was taken when there was a seaward directed event. The wind forcing was in the opposite direction. And you'll see that there are current speeds that peak at a meter per second in the opposite direction. The tidal currents, if I remember correctly, Jesper can correct me, are sort of only in the sort of a decimeter or two per second. You know, they're very, very weak tidal currents in this system. So the dominant energy in this for sediment transport and for the construction of the sediment bodies is, in fact, meteorological forcing. Now, this example was an anomaly in my database, but I put it in on purpose. This is a freshwater strait. This is a strait between two of the Great Lakes. Lakes Michigan and Huron are both at exactly the same elevation. This is not a river connecting them, it's a strait. And it's a rather complicated pathway here. And there have been extensive current meter data collected in this strait. So here, I've blanked out the horizontal axis on purpose, but I will reveal it in a minute. This is the current meter record. You don't know the time scale, just like you don't know the time scale when you measure bundle thickness in the rock record. Does that look tidal? Spring tides, neap tides, spring tide, neap tides, spring tide, neap tides, etc., etc. Tides in the Great Lakes? Could this be a tidal signature? Well, there's the time scale. This spans about half a year. And the bottom diagram is the energy density as a function of period. There is no energy at tidal periods. That may look like a tidal signature, but it's entirely meteorological. It has to do with these various peaks here, here, and here are related to the siege period of the lakes. It's related to how long it takes atmospheric depressions, the low pressure systems to move through the area. The higher velocities here are in the winter when the storms are more intense. Those smaller ones here are over the summer when the storms are less intense. So, cross-bedding. Cross-bedding in straits commonly shows some type of rhythmic or bundle-like organization. And it's quite common for these to be interpreted as some kind of tidal signature. Most such deposits are not usually as regular as this particular diagram from Sergio and work earlier on. they must have been very lucky or just maybe drew it that way. But is this tidal? It's possible, however, that this kind of bundling with the presence of reactivation surfaces, changes in grain size and grain composition, could be due to meteorological currents of the type that I've illustrated in the previous talk. In the field guide for our Bonifacio trip, Jean-Yves and Michel have suggested that in fact the amount of migration that is required to get these bundles is more than is conceivable for a dune of these sorts of sizes. So I think then that tidal has been overemphasized. So I see that I'm running out of time. I get carried away with things, but unidirectional currents, in terms of interpreting these ancient deposits, how should we interpret unidirectional paleocurrents? Well, they may be due to the presence of density-driven or oceanic currents acting together with tidal or meteorological currents, or they could be simply due to the presence of tidal asymmetry. Menai Strait at Bangor, out here in Wales, has unidirectional transport along its entire length due to phase differences in the tide between the two ends of the strait. What about the reactivation surfaces that are so common in here? Are they due to current reversals? Yes, that's certainly possible, but we have to remember that they could be formed by overriding dunes, wave action, or a number of other factors. So that I think that there has been a tendency in at least some studies to jump to a tidal interpretation without considering all possible possibilities. So the architecture of the deposits. Sergio has done a good job of describing the deposits that are forming where the sediment comes out of places such as Golden Gate Inlet or the Messina Strait. Other straits have similar kinds of bodies, like the Minas Passage, Minas Channel has a little bit of one of these, what I refer to as a constriction-related delta, but it's very patchy. There's deposits there, some in there and there, but it's not a continuous lobate body because of the strong scour erosion. Something similar exists in Cook Inlet. So these sorts of deltas are present, but the examples that Sergio has chosen are the best examples that I have found. So he was either very lucky or very good at choosing the supporting examples. And what I found very interesting is that the bedform distribution that he showed in this diagram is identical to the bedform distribution that was recognized in the English Channel and Southern North Sea by Belderson et al. 40 years ago. In this diagram, the other thing I would point out is that Sergio shows these two deltas as being symmetrical. That is never the case that in the examples that I have looked at. So even, I suspect, although I might get an argument on this one, is that these appear to be asymmetrical with a much larger northern one in Messina Strait, perhaps because of the overprinting of the density circulation that exists in this system. In terms of their architecture, I can't find a single common thread to any of the examples that I found. If the deposits are relatively coarse-grained, and commonly if they're carbonate, the deltas that are formed tend to be relatively high-angle cliniforms. So that there's this example by Nelson in New Zealand, there's this example off the western tip of Sicily that was described recently by Schlutman et al., with these large-scale 50-meter high cliniforms that are formed. Things that are in the carbonate literature are referred to as carbonate deltas. but many of the examples that I've seen probably don't show that. And just to sort of hypothesize about the range of possible variation here, I want to look a little bit closer at the Golden Gate example. And I've got a red line here that illustrates kind of the section that I suspect is shown in this simplified diagram. Current speed decreases as you move outwards from the constriction. This leads to deposition. That causes the dunes to climb. And because of the climbing, the dunes become smaller as you move outwards away from the constriction. And so that's exactly what's happening along that line. However, the dunes at the end of this are going to eventually slow down to the point where they stop moving. So let's look at this line now, where the termination of the delta lobe is very different. It ends with this anomalously large dune. So I've kind of tried to illustrate that here, that dune stalls. The next dune along overrides it and amalgamates with it, and eventually you end up building an anomalously large dune at the downstream end of the transport path, which seems to be what we have had happen here. Now, why this delta should have two different behaviors so close together, I have no idea, but it's obvious that that is happening. And that's been documented in the ancient. Another example that I found very interesting is this work by Reno, and it turns out that Dalrymple has to be the E of the et al. In this, so I have to take some responsibility. We referred to this body in here as a flood tidal delta. And yes, it is. It's formed by the flood tide moving through this narrow passageway. But in the new way of looking at things, that's a strait. And this is a constriction-related delta, so it provides what I think is one of the very good descriptions of what the architecture of a constriction-related delta might be, with straight axis, high, large-scale dunes down here, backset climbing bedding formed as the dunes move into lower energy. They built up the crest of the lobe, and some of them have spilled over in this side. So this is just one possible expression of these bodies. So I know I'm out of time, so I'll just go very quickly through this. If the strait is shallow enough, in other words, its base was exposed at the low stand, then I suggest that there is a predictable pattern of environmental evolution. And that's shown in the diagram on the right, which is shown as being cyclic. At low stand, Malacca Strait and the English Channel are two examples that both have rivers that flowed along their axis at low stand. And they develop deltas at the low stand shoreline. And that is shown best here in Malacca Strait, where the outline of the delta can still be seen in the morphology. In the early transgression, which is shown there, you create estuaries, and that has been documented best in Menai Strait, where the delta at the northern end was a tide-dominated funnel-shaped estuary that graded as sea level rose, and at this other end there was a wave-dominated estuary, and eventually only in the last few thousand years has water level risen high enough to actually cause things to join. Eventually you form some kind of an embayment, and just as an example, I've simply outlined a 50-meter isobath here in the English Channel to show what might have happened at some point in the early Holocene. And as sea level rose, we eventually connect through to give a through-going strait. And if there's enough sediment supply, probably unusual, Malacca Strait provides the only example that I'm aware of, then sediment can be supplied by the deltas from the side that can build into the strait and have the potential to choke it off and have deltas begin to prograde down the axis of the strait. So I'll have you look at the paper to go through this sort of conceptual model of what a full succession might be. I think it's highly unlikely that it is preserved in its entirety. One of the major things that might happen is at the time of maximum current strength, you might generate a significant scour surface that removes most of the older deposits. And I think that many of these erosional deeps, like here or here in Cook Strait, are examples of those deeply scoured erosion surfaces that have the potential to be misinterpreted as sequence boundaries. So, straits there is no common one type of strait. They're highly variable. 4 types of currents. I think that meteorological currents have been underappreciated in straits and need to be considered much more upfront in interpreting the deposits. These constriction-related deltas are probably the main site of deposition, and Sergio's model is as good as any. In fact, it's by far the best one for maybe having a stab at trying to understand the evolution of these bodies. But I'm calling them constriction-related deltas. The volume of these deltas is probably limited in siliciclastic systems because it's difficult to erode the sea floor. They will be larger in carbonate systems because of the production of sediment within the body of the strait. There is this predictable, I suggest, evolution for shallow straits. The time of maximum current speed can generate a significant erosion surface that must be an integral part of the succession. And we need more examples. We just simply don't have enough examples of any of this. And even though my review is as exhaustive as any has been attempted so far, I'm sure it has not encompassed the entire variability that exists. There is an overwhelming amount of work that must still be done to understand straits. Thank you.
Questions?
Thank you, Bob, for showing my hometown. In the straits, you have very large bodies of water moving. I'm surprised you haven't mentioned the Coriolis floors once.
Yes. If you read my paper, you will see that there are several pages explaining the 2 types of Rossby radius and how shelf or strait width, defining the difference between, in fact, in the paper, my way of describing or just delimiting between narrow and wide straits is whether the width is more or less than the Rossby radius. Because if the strait is narrower than the Rossby radius, there will be one flow direction through the entire strait width. But if it's wider than the Rossby radius, you can have 2 directions of flow on opposite sides. And Bering Strait's kind of just at the border, even though it's fairly far north and the Rossby radius is relatively small. So I just simply didn't have time. If you'd given me a whole day, it would definitely have been considered.
Your excuse. I think perhaps it could be one of the explanations for the example you mentioned, the large sediment body in one end and not in the other. I don't know.
Well, that's side to side of the current, not end to end of the current.
But still, we see that even if in inlets to the water sea, it's wide enough.
Yeah. I'm sure. Many people forget that we're living on a rotating orb in the cosmos.
Especially as we get north. Okay, good.
We have time for one more question.
I really particularly enjoyed your freshwater lake example where you took away the axis for the time scale. I was just wondering if we see, or if we think we see any bubbling, what would be your advice to kind of assess their formation time scale?
I have thought about this, and all I can suggest is looking at the degree of regularity. The meteorological signals should, like the Bering Strait example, be stochastic at some level. Unfortunately, that lake example kind of blows that out of the water. Because there is a siege that is of a predictable length, that becomes much more tide-like in its character. And the suggestion that I have is that a tide, most tides are semi-diurnal, 6 hours, or diurnal, less commonly, 12. And the amount of sediment that can be transported in that amount of time is less than can be transported in, say, 3 days, or 1 day, or 2 days. So that if it's a meteorological signal, the bundles may be larger than the bundles formed by tides. But because we have no benchmark for knowing what the thickness of a bundle should be for a particular dune in a particular setting, I'm not sure that this advice is easily followed. And this is an important question for those working in the ancient.
Thank you, Bob. Do you think that a same strait may experience some change in the regimes of currents? I mean, could a single strait may pass from tidal dominated to meteorological dominated, or vice versa, and so on?
I think the overriding thing that influences my answer is having looked at 33 straits and seeing the amount of variability. My answer is basically anything's possible, as long as it doesn't violate physics or chemical whatever laws that are relevant. Changing the tide is difficult because, as you know, the tide is governed by the larger scale geomorphology of the system. So that you have to change the larger scale geomorphology of the system to change the tide significantly. Of course, with lagoons and tidal inlets, that's rather easy because the morphology is very dynamic. But if it's like Messina and it's all structural, that's going to happen much more slowly. Meteorology can be changed quite dramatically on decadal or other time scales. So if you're at one of these tipping points, so the slight increase in storminess might well make meteorological currents more important than they were before. It might tip the balance, but it still will be a mixed energy system. I would expect the frequency distribution of bundle thickness to be very noisy. There's no strong peaks. But I'm flapping my arms because I don't have a specific answer.
Let's continue this over the break. Thank you so much for